All right, physics, welcome to another flipped lecture. We're talking today about chapter 16A, which is about we're introducing the concept of thermodynamics to you in chapter 16. 16A deals with the first two laws of thermodynamics. Interestingly, the first one is called the zeroth law because it was discovered later or described later than the first law, and everybody was already calling the first law the first law. So they're like, oh, what do we call this? Let's call it the zeroth law. So we're going to be looking at that one and the first law of thermodynamics today, and then the second and third laws come to you next week. So without any further ado, let's get into it. Alrighty, so we're talking about heat in the concept of thermodynamics. Thermo meaning heat energy or thermal energy, dynamic meaning it changes or it flows. So we're looking at how heat flows. The concept of thermal energy and temperature is related to motion. We already talked about that, and so thermal energy is always motion at the atomic level, atoms and molecules vibrating or flowing or moving in some way. When we talk about how much energy something has internally, it's hard to describe, but the best we can do is to look at how that energy changes. Total internal energy is we use a capital U to represent that in equations, but it's impossible to know at any particular moment in time how much every atom or molecule in a substance is moving. That's just too much data to gather at one time. And so we never know truly the actual total internal energy, but we can look at how the temperature of something changes, and we can determine from that change how much energy change there has been. And we can guess as to how much total energy there is in the thing, but it's always an approximation. The best measurement that we can take is looking at changing temperature, changing thermal energy in a substance. Couple of vocabulary words for you here. If something is a barrier to thermal energy flow, it's a thermal insulator. Then we use the word adiabatic. Why? I don't know, but that's what it means. Adiabatic means temperature, thermal energy, heat cannot go across that material. So good examples of adiabatic materials would be like a vacuum flask, or less exact with the same idea like a styrofoam cup or a styrofoam cooler. Something with a lot of trapped air or no air at all is a good adiabatic material. The opposite of that is a diathermic, which is something that conducts heat energy well. So examples of this would be most metals, especially copper. Copper is a great heat conductor. That's why the best, most expensive cooking pots are copper, because it lets the heat travel through very, very quickly. Okay, so diathermic means heat moves through it. Adiabatic means Now, we're getting close to being able to describe the zeroth law, but first we've got to talk about heat flow real quickly. When two substances are put in contact with each other or next to each other, and one is hotter than the other, heat flow is going to happen. And at some point, we're going to get to a place where everything is the same temperature. So, you know, in your experience, you take a nice cold glass of water, take a couple of sips, put it down on the table, forget about it. In, I don't know, 20, 30 minutes, you're like, oh, there's that glass of water. And you walk over there and it's not cold anymore. It's room temperature. And that's because the water has gotten to a state of equilibrium with the thermal energy in it and the thermal energy in the air and the room and the table and the glass and all kinds of other things around it. So thermal equilibrium means that everything has the same amount of thermal energy. It's the same temperature as everything else around it. Thermal energy always goes from a substance with higher thermal energy, something that's hotter, to a substance with lower thermal energy, something that's colder. And we call that flow of thermal energy heat. So if something is hot, you know that because it's giving you thermal energy. And you say, wow, that's hot. But it's the flow of the thermal energy that we call heat. So use an example as like water. Water being piled up behind a dam. That water, we could consider that a reservoir of thermal energy. And then down at the bottom of the dam, there's a gate that can open and let water out. Well, that rushing water out of the reservoir would be like heat. It's the thermal energy leaving someplace where there's a lot of it and going to a place where there's not as much. Okay, so thermal energy flowing is heat. So that brings us to the 0th law of thermodynamics. Two systems that are in equilibrium with the third system are in equilibrium with each other. So if this box of Kleenex is the same temperature as the air around it, which it probably is, and this box of Kleenex is the same temperature as the desk that it's on, then I could say that the air and the desk are the same temperature, because the one thing is in equilibrium with two other systems, and so those two systems must be in equilibrium with each other. And that's very, very similar to the transitive property of algebra. So that's something you can identify this with, where if A equals B and B equals C, then A equals C, right? Same thing is true with thermal energy. If A has as much thermal energy as B and B has as much thermal energy as C, then A and C also have the same amount of thermal energy. All right, so that's the 0th law. And here, let's give you a picture of it. There you go. So the 0th law of thermodynamics, if A and C are in equilibrium and B and C are in equilibrium across a diathermic barrier, meaning it conducts electricity, conducts heat energy, then C, being in equilibrium with both A and B, means that A and B are in equilibrium with each other, right? And so the idea here is that, again, it's like the transitive property. If this equals this and this equals this, then these two have to equal each other. Okay? Hope that makes sense. So that's the 0th law. Let's look at the first law. The first law of thermodynamics, which was actually discovered first, hence it's got its name, but then we've discovered that the 0th law is more fundamental. The first law of thermodynamics is that energy can be added to a system, which would be a change in the total internal energy, change in U, either by mechanical work done on the surroundings by some unbalanced force, and we say that that's change in W for like work, right? But notice it's a negative W because we're looking at what change happens to the surroundings, not what change happens to the system. So we put a little negative sign in front of that, okay? Or by heat transfer. Q, remember, is thermal energy. So change in Q from the outside of the system. So we can energize the system either by putting some forces on it so that it does work on the environment, or we can add some heat to it. Either way, there's going to be a change in the internal energy of that system. The conservation of mechanical energy is expanded to include thermal energy, and so we can call that the second law of thermodynamics. And here we have delta Q. I was about to point on my screen, that wouldn't have helped you. Delta Q, the change in thermal energy, is equal to a change in total internal energy plus a change in work. Now, the first law was describing a change in U, and then said these two things can change U. And then when we look at it written out as an equation, it's not U equals Q plus W, it's Q equals U plus W. And then you think to yourself, why isn't it U equals Q plus W? Because we're talking about U, aren't we? But then realize this is negative. So then rather than writing U equals Q minus W, which is what this would be, U equals Q minus W, they wanted to write it with an addition sign instead of a subtraction. So they moved W over. So now it's Q equals U plus W. Understand that that's algebraically the same thing, okay? So a change in heat energy is equal to a change in total energy and a change in work, okay? So you can have U equals Q minus W if you'd like, and you can use that just as well. No problem at all. So let's look at an example here. Energy before some change happened is equal to energy after some change happened, okay? There's always a conservation of energy here. It's going to be the same. We might have chemical energy here, we might have thermal energy over here, and then after the reaction, if we were to look at all the energy available before and all the energy that we got afterwards, It's the same thing. Conservation of energy states that the same amount of energy is present in any form. Okay, so let's talk about how we use these fundamental laws of thermodynamics. We use them most often with regard to heat engines. Heat engines are machines that allow heat to change something, and that change in something does some useful work. Most of the time, it's a change in gas, because gases like to expand when they get hot and shrink when they get cold. And so if we use heat to change the volume of a gas, we can use that expanding gas to do work. So usually that's the example, okay? The best example that we're all going to be familiar with is a cylinder and a piston in an engine. The oxygen, or the outside air, and the spray of gasoline go into a very small space, and then a spark explosion, and the explosion causes the gas to expand. That expanding gas drives down a piston, which pushes the crankshaft of the engine and makes your wheels turn, and down the road you go, right? So that idea is a heat engine. We're using heat to do mechanical work. And thermodynamics explains how this works. Again, we're looking at work done on the surroundings, not work done on the gas. So think again about that example. Air, gasoline spray, spark. I don't care about what work was done by the engine on the gas. I care about what that expanding gas can do on my engine. So it's always work on the surroundings, not work on the gas. Keep that straight as we're doing this work. Okay, so the work on the surroundings is proportional to changes in pressure and volume in the system. So we have work on the surroundings is equal to pressure times the change in volume. The easiest way to solve for W is to do it graphically with a PV graph, and I'll show you that in a moment, how to work that. And the work done, if you have a PV graph, is equal to the area under the curve. So this is where we're going to only be using straight lines, because not all of you have taken calculus. Actually, none of you have taken true calculus. Some of you are in pre-calculus, and you need calculus to calculate the area under a curve, to be honestly the area under a curve. Algebra will let you calculate the area under a line or some algebraic function, but not crazy curvatures. So for that you need calculus, which is why Isaac Newton, who came up with this sort of science, also came up with calculus, because he realized he needed a different mathematical tool to do this kind of work. So this is why calculus was born, was to answer this kind of question. But we're going to keep lines straight for you in algebra, and that will help move this class along a little bit nicer. Okay, so let's look at some examples. Here, I have again the example of a piston and a cylinder in an engine. Okay, in one cycle, an engine's piston with a surface area of 28 square centimeters drops from 1 centimeter below the spark plug to 5 centimeters below the plug. So it's only 1 centimeter below the plug, then the explosion happens and it gets driven down to 5 centimeters below the plug. Okay, we're going to assume, for ease of use in this example, that the pressure is kept constant at 1 Pascal. So 1 Pascal at the whole time. Obviously there's an increase in pressure, which is what causes the piston to drop, but we're going to ignore the inconsistency in pressure for the sake of this example, and we're just going to say that the piston drops perfectly to keep the pressure always at 1 Pascal. Okay, just to simplify the things for this example. So how much work does the gas inside the chamber do on the piston and therefore on the engine? Work equals pressure times the change in volume. Okay, my pressure is 1 Pascal. My volume I have to work out. So first we need the change in volume. The volume 1 is a cylindrical airspace with a surface area of 28 square centimeters and a height of 1 centimeter. So 28 times 1, the volume of that cylinder is 28 cubic centimeters. Now, V2, the second volume, would be that same 28 square centimeters, but having been pushed down to 5 centimeters below the spark plug. Now we have 28 times 5. So my volume of the air mass there is 140 cubic centimeters. So change in volume equals 140 minus 28, or 112 cubic centimeters. This equation requires that delta V be in terms of cubic meters, not cubic centimeters, so we have to do some conversions here, okay? So 112 cubic centimeters, and then we have to go to cubic meters. There are 1,000,000 cubic centimeters in a cubic meter, giving me 0.000112 cubic meters is my volume. So I need to have it in cubic meters. So work equals 1 Pascal times this. This times 1 is that. We need to adjust for sig figs and to check the sign of the answer. So since the gas got bigger, the work was done on the system around it, so there should be positive work done on the system. So my answer should be positive, and I need to adjust for significant digits. Here I have 2 significant digits and 2 significant digits. 2, 2, 2, everywhere I look it's 2, so 2 significant digits is my answer. The gas did 0.0011 joules of work on the piston. Alrighty, so now we're going to look at how to solve one of these equations with a PV graph, okay? We solve for W graphically, and it's just the area under the curve of a pressure volume graph. Now, in order to make it easy, the graph should be in pascals versus cubic meters. If you have any other units, you need to do conversions, because a joule is a pascal times a cubic meter. That will give you a joule. If you have, like an example, we're going to have cubic centimeters, or cubic millimeters actually, and then liters. So you have to mess with the units a little bit. But if you can graph it in pascals versus cubic meters, it's just an area question. So that's pretty simple. Let me show you an example. So we have an example here that is asking us to create a pressure and volume graph. And it's not in the ideal units though. It's in 10 to the 5th pascals, so way more than 1 Pascal. And it is in liters, which is way less than a cubic meter. However, the good news is that the ratio winds up being the same. So there are a lot fewer liters there are a lot of liters in a cubic meter, and there's a lot of pascals in 10 to the 5th pascals, and the ratio balances. So in this particular example, it still comes out as joules. But that's just because we're lucky for this example. So gas originally at 10 times 10 to the 5th pascals and 1 liter expands it until it is in volume 2 liters, and its pressure is half, 0.5 times 10 to the 5th pascals. How much work is done by the gas? So the gas in the cylinder is the system, and the work is going to be relative to the system surroundings. So we're going to be looking at work done on the surroundings by the system. And so we are going to, we need to figure out, well, first we would need to graph it. So here's what it looks like. 1 times 10 to the 5th pascals down to a half times 10 to the 5th pascals. And then we need to carry that down to 0. And then the volume went from 1 liter to 2 liters. So it is 1 liter by half a Pascal for here, okay? And then 1 liter by another half a Pascal, but that's a triangle. All you have to do is get the area. So treat these like shapes. It's 1 by 0.5, right? And so we can multiply this across and get 25 Newton meters, which then is the same as 25 joules for the area of a triangle. And then the area of the rectangle is 1 times half of a Pascal times 10 to the 5th. Multiply that across and convert, and that gives us 50 joules. So 25 joules and 50 joules, 50 joules, 25 joules, you add it up, you get 75 joules. So the area under the curve is 75 joules, and that is a very easy way to go about solving these kinds of problems, as long as you can convert the units that you've given to pascals and cubic meters. Okay, moving on. This last slide is just a combination of a whole bunch of vocabulary words at the end of 16A that you need to be able to understand the questions that are going to be thrown at you. So the terms here, The first three have to do with the kind of system you're looking at. An open system is a system where you're looking at something, but matter and energy can come in and out of it. So like if you're watching an ice cube melt on a table, matter and energy can enter and exit your system. The energy, obviously, from the room is coming in and heating up the ice and giving it the energy to melt. And so energy is entering your system, and then as the water melts, it might run off the edge of the table and go away. So that system does not contain matter or energy. Energy and matter can come and go from it. That's an open system. A closed system keeps all the matter in one place, but lets energy come or go. And so that might be if I'm watching an ice cube melt inside a glass. So now the glass is going to contain all the matter, and we might put some kind of screen or something on the top to keep the water vapor in. But the energy is still going to come in from the room and melt the glass of water, melt the ice cube, sorry, in the glass and make it water. So that would be a closed system. It's closed to matter, but energy can still come and go. The last is where it's closed to both energy and matter in a system where no energy can come or go and no matter can come or go. And that would be a isolated system. An example of that would be putting a bunch of ice in a hydro flask and shutting the lid. You know, a hydro flask isn't perfect, but let's imagine that it is. That's a perfect hydro flask. And then when you do that, no thermal energy can come or go, and no matter can come or go. And that ice is going to maybe melt a little bit because there's some thermal energy in the air around the ice cubes, but it's not going to melt very much. And once everything reaches thermal equilibrium, it'll stay that way, theoretically, forever, right? So that's an isolated system. Then we have the word adiabatic. We've already talked about that. That is a barrier. An adiabatic barrier blocks thermal energy from flowing. An adiabatic process is a process where no thermal energy leaves or enters the system, where you just have the thermal energy that you're dealing with in the system. An isothermal process is a process where the temperature does not change, okay? Thermal energy may flow, but it's only going to be latent heat. It's not going to change the temperature of the system. Isochoric processes you're looking at a volume of gas and the volume does not change. Well, if the volume of the gas does not change, then it can't do any work on its surroundings. So those really aren't very helpful questions, very helpful situations. You won't do much of that in this unit. Isobaric processes, though, hold pressure constant. So as the temperature goes up and down and the volume responds, it just keeps the pressure the same the whole time. So you should be hearing echoes of like ideal gas law from chemistry in your head with relationships of temperature and pressure and volume. That's this section in a nutshell. We'll talk about it in class. Let me know if you have any questions. You can put them in the comments field below and I'll get to it as quickly as I can. God bless you. Have a wonderful day.